Hey everyone, today we're diving into something that sounds super academic, but I promise you, it's not. We're talking about the design and analysis of algorithms. And trust me, this is way more than just theory. We're going to treat it as what it really is, the ultimate problem-solving toolkit. So let me ask you this. Sorting 10 books on your shelf? That's easy, right? You do it. But what if you had to sort 10 million books for a massive digital library? Whoa. All of a sudden, how you choose to do it becomes everything. The right way could take seconds. The wrong way could literally take years. And that, right there, is the core reason we need to talk about algorithms. So what even is an algorithm when we get right down to it? Well, the best way to think about it is like a recipe for baking a cake, or maybe the blueprint for building a house. It's the detailed step-by-step plan. It's not the actual cake you get to eat, and it's not the physical house you live in. It's just the set of instructions you follow to get the result. It's the logic, the strategy, the big idea. And this brings us to a really, really important distinction that trips a lot of people up. An algorithm is not a program. Think about it. The algorithm is the blueprint. It's an abstract idea that doesn't care what programming language you use or what computer you're on. A program, on the other hand, is the actual building. It's the concrete thing you write in, say, Python or Java that runs on your specific hardware. We analyze the blueprint first to make sure the building is going to be strong and efficient before we even lay a single brick of code. All right, here's our game plan for today. We're going to tackle the core challenge. Then we'll look at how to measure efficiency with something I call the efficiency ruler. After that, we'll open up the designer's toolkit, see how to pick the right tool for the job, and finally, we'll take a peek at some problems that are right on the very edge of what's possible. Okay, let's jump right in. What's the fundamental challenge here? Well, for any problem you can think of, like sorting those 10 million books, there are probably dozens of different ways to do it. So how on earth do you figure out which one is the best? And here's the thing. Best isn't just about being correct. I mean, any working algorithm will get you the right answer, eventually. The real game is all about efficiency. You see, every algorithm consumes two critical resources: time, how long it takes to run, and space, how much memory it needs. And what you find is this constant trade-off. An algorithm might be incredibly fast, but be a total memory hog. Or it could be super light on memory, but take forever to run. Our job is to find that sweet spot. Okay, so if we need to find the most efficient algorithm, we obviously need a way to measure them. But how do you do that in a way that's actually fair? Now, you might think, let's just use a stopwatch. But that's a terrible idea. Why? Because a super fast computer can make a really bad algorithm look good. We need a universal, hardware-independent ruler. And for that, we borrowed this brilliant tool for mathematics called asymptotic notations. It's just a fancy way of describing how an algorithm's performance scales as the size of the problem gets bigger and bigger. And I absolutely love this analogy to explain them. Think of it like a prophecy about a lifespan. Big O, which is the one you'll hear about the most, is the worst-case scenario. The prophecy says you will live at most 70 years. It's your upper limit. Then there's Big Omega, the best-case scenario. You will live at least 30 years. And finally, Theta, which gives you a tight range. You'll live around 50 years. In computer science, we often focus on Big O, the worst case, because it tells us the absolute maximum challenge our algorithm will face. It lets us say that one sorting method is O of n squared, where time just explodes with more books, while another is O of n log n, which stays way faster at scale. And that is the difference between seconds and years. Now that we've got our efficiency ruler, it's time to open up the toolkit itself and look at some of the power tools, the common strategies that designers use to build these solutions. Inside this toolkit, we find all these powerful strategies. You've got divide and conquer, greedy algorithms, dynamic programming, and a whole bunch more. Each of these is a different approach, a different way of thinking about a problem, and each one is suited for a different class of challenges. We can't cover all of them today, so let's just zoom in on an absolute classic to see how these strategies work: divide and conquer. The logic here is just brilliantly simple. First, you divide a huge, intimidating problem into smaller, more manageable pieces. Second, you conquer by solving those smaller subproblems, often by just applying the same logic over and over. And finally, you combine the solutions from all those little pieces to get the final answer for the original big problem. So many famous algorithms, like merge sort, are built on this powerful idea. So knowing the strategies is one thing, but how do you pick the right one? Let's check out another tool, the greedy approach, with a really concrete example. A greedy algorithm is, well, it's pretty much what it sounds like. At every single step, it makes the choice that looks best right now, without worrying about what might happen down the road. It's all about making that locally optimal choice and just hoping it leads to a globally great solution. This slide illustrates the idea perfectly. How do you make 67 cents and change with the fewest coins? The greedy approach is simple. Always take the biggest coin you can. So first, a quarter. Now we have 42 cents left. Let's take another quarter. Okay, 17 cents left. Now a dime, then a nickel, and finally 2 pennies. Boom, done. In this case, making the best local choice at each step actually led to the perfect overall solution. We've seen how to build and measure solutions, but for our last section, let's look at the frontier. Because it turns out that even with the best tools and the fastest computers, some problems are just fundamentally monstrously hard. And this is where we get into this fascinating distinction that computer scientists make. It's the difference between problems that are easy to solve from scratch and problems where if someone just gives you the answer, it's really easy to check if they're right. This leads to two of the most famous categories in all of science. You've got class P for problems that are fast to solve. P stands for polynomial time, but just think fast. Sorting a list is a classic P problem. Then you have class NP. These are problems that are fast to check. Finding the shortest route to visit 100 cities is ridiculously hard to solve. But if I give you a proposed route, you can check its total distance in a snap. That's an NP problem. So here it is, the million-dollar question. Literally, there's a prize. Are these two classes of problems actually different? Or could it be that every problem that's easy to check, all those NP problems, are also secretly easy to solve, and we just haven't been clever enough to find the algorithm yet? This is the P versus NP problem, maybe the most famous unsolved question in all of computer science. So why does this matter so much? Well, if P does equal NP, the entire world would change overnight. I am not exaggerating. Think about the hardest problems we face: designing a new protein to cure a disease, creating a perfectly optimal logistics network for the whole planet, breaking modern encryption. These are all NP problems. If P equals NP, it means a hidden, fast shortcut exists for all of them. It would turn these monumental challenges into homework problems. So, what's the big takeaway here? An algorithm isn't just a piece of code. It's a fundamental way of thinking. It's about breaking down complexity, measuring efficiency, choosing the right strategy for the fight, and understanding the very limits of what's possible to solve. It is, without a doubt, the ultimate problem-solving toolkit.